since I'm really a person that works mostly in ADS-CFT, I thought about what to work on, to talk about, and I decided to talk about the work that is mostly in progress, but one paper, so one half of this, has already appeared like a week ago or so. It's about Krylov complexity and its relation to circuit complexity and to instantons. Oops, sorry. So first I will tell you a little bit about notions of complexity, and in particular about Krylov complexity, then relate it to circuit complexity, and then to instantons, specifically by making a path integral formula available and showing that this relates to some sort of instantons. And we started testing this in some toy model, and I will tell you some preliminary results. So first, complexity is really a measure of a calculation, and in a quantum mechanical case, this is a measure of how a generic state evolves in time. Now, circuit complexity, which is the notion that really extends the classical complexity of a computation, is one that appeared first. Then another notion of complexity provided by Nielsen was a sort of geometric notion on a space of Hamiltonians. But then the notion that is easiest to calculate with, the one that is truly algorithmic, is this Krylov complexity, because it's based on the line source algorithm to obtain a certain quantum state basis, from which we just use a formula. Now, in holography, of course, we have various formulae, complexity equal action, equal volume, and equal anything, quotation marks. So that is also another set of formulas, but I will not be talking about that except to mention them very quickly. So the first part of the talk will be to relate this algorithmic Krylov complexity to the circuit complexity, which means really something that you can construct using quantum circuits. But then we'll also show, since other people showed that the Krylov and Nielsen complexities are related, therefore, Nielsen complexity can also be related to circuit complexity and have basically a single notion, even though different ways of calculating it are available. Now, the complexity, and in particular the one defined by Krylov, by the Krylov algorithm, is assumed to have a late time plateau, so meaning that as the complexity increases in time, at some point this starts to taper off, and then there's a plateau. But at least this behavior is assumed to happen in the case of a chaotic system. And we show how this could happen, and we conjecture a formula with a sort of instanton factor that can appear. And then finally, we'll consider a toy model of just two harmonic oscillators coupled with an exponentially increasing interaction, such that we have a chaotic system, and we can test these ideas. All right, so what are these various notions of complexity? The classical notion of complexity is something very simple. You just start with some initial state, a bunch of zeros and one, end up with a final state, another bunch of zeros and one, and there's a computation that takes you from one to the other. And basically, the complexity is the minimum number of gates, the ones available to the computer, to take you from one state to the other. In the quantum case, quantum mechanics is unitary, so we have a unitary operation taking us from an initial state to a final state. One extra factor is the fact that in the quantum case, the unitary transformations are continuous. So you cannot always go from, excuse me, from an arbitrary initial state to an arbitrary final state by a finite number of discrete gates. But rather, we assume in general that there should be a tolerance with which we should obtain the final state. Tolerance epsilon. But otherwise, it's the same idea, the number of gates that takes us from an initial to a final state. Excuse me. So this is a generic notion, but in particular, Nielsen came up with an approach that is more geometric and easier. Oh, thank you. It's more geometric and easier to understand. Excuse me. So we define the unitary transformation as coming from quote-unquote Hamiltonian, an object defined in a spin chain type in a certain operator basis. So it can either be spin up, spin down, or Pauli sigma matrices, or it can be something more general. But so there's some basis for the Hamiltonian. And then there's there are certain coefficients, and one integrates over this position S from, let's say, from 0 to S, and then one obtains a Schrödinger equation. Excuse me. Yeah, so in principle, I mean, I said spin chain. It could be any spin chain. It doesn't need to be near neighbor interaction in principle. But this is also it's an action in an abstract space. So we're talking here when we're thinking of these sigmas, we're thinking of them as qubits. So like in the classical computation case, you had zeros and ones. Now you have spins ones and spins ups and spin downs, and you just have a set of qubits, initial state, and the final state. Oh, yeah. This depends. Yeah, there's no necessary notion for that in principle. It could be, and in the cases we're interested in, perhaps we're thinking of something like that. But in general, it doesn't need to be, because what you're doing to a computer, you're inputting a set of zeros and one, or qubits, and you're outputting another set of qubits. So in principle, the computation doesn't need to be local in any sense. Oh, it's not a k going to infinity. Yeah, it's just a finite. Yeah. We'll okay. Let's get to the next part. So there is, in general, something that needs to be minimized. So one considers something called a cost function, something that depends on the parameters that multiply the Hamiltonian. And then this is minimized and integrated over a certain, so integrated from 0 to 1. And the minimum of this distance, quote unquote, is the complexity. So that's sort of a geometric notion on this space of Hamiltonians that you're minimizing the distance, and the complexity is the minimum of that distance. And then Nielsen made this a little bit more precise, that if you can think of this as Riemannian space with this metric, then really the complexity is the geodesic, the length of the geodesic. In the end, yes, we'll show, but initially it was not, the relation was not explicit, yeah. I will, well, implicitly, but yes, I will show. I'm sorry? What defines the metric? So exactly this notion. So basically the yi's are defining the metric. The optimal. Yeah. You're optimizing. It's like you know, you have various lengths on a space, and the minimum, the geodesic, is the complexity. Yeah. All right, but the notion that I'm mostly interested in is the notion of Krylov complexity, also called, well, in a more general sense, spread complexity. The point is, one has to define first a basis of states that are defined from an algorithm known as the Lanczos algorithm. The basis of state starts with a reference state, the initial state, and then acting many times with the Hamiltonian. Let's say there's a real Hamiltonian now for time evolution, and uses the Gram-Schmidt orthogonalization procedure on the action of n time action of Hamiltonian. Then finally, once all is finished, the Hamiltonian is now, one obtains a basis Kn known as the Krylov basis, and the Hamiltonian takes this tridiagonal form in this basis. And then finally, in this basis, one constructs the Krylov complexity in this way. So is sum over n of n times the probability of the time evolving state to be in the basis Kn. And this is conjectured to have, at least in the chaotic case, to have a plateau at large times, just as the other notions of complexity are also assumed to have this. All right. So in the first work, we tried to relate the notion of Krylov complexity with the notion of circuit complexity, of ones involving action of circuits and unitary gates. But first, yeah, actually, I don't think I want to talk about this. I don't know why I put this. But let's forget about holography. Anyway, since the audience here is mixed, it doesn't matter. Then there's a relation between Krylov and Nielsen complexity that was found by these people. So if we have a motion on a Lie algebra, so on a group, rather, I should say, from the Hamiltonian, one constructs an action via this operator alpha times L plus and L minus, or L plus and minus are two operators in the Lie algebra that are raising and lowering type. Then with the displacement operator, the one that shifts a position, defined in this way. Well, not necessarily. I mean, you just write a linear combination. So this would be like A plus A dagger, if you want, right? No, H is really the Hamiltonian, but you have to think of it as a Hamiltonian of the type A plus A dagger. And it could also, later on, there's a generalization I'll just write, where you write also the commutator of A and A dagger, which can appear. That's right, yeah, yeah. Yeah. The displacement operator acts in this way, and then one generates some coherent states by acting with this displacement operator on something that like a vacuum, which can be perhaps a highest weight state, depending on the type of group that we have. And then the geometry defined by defined by these coherent states is the so-called information metric of the Fubini study type defined in here. And using this metric, GZZ bar, one can define first a classical version of the Hamiltonian operator by acting on Z's, and then define also Poisson brackets with the same, the inverse metric in here. And that reduces the evolution on the coherent states to these classical looking Poisson equations. So that defines a trajectory in the Hilbert space of coherent states Z. And then that is, in fact, identified with the geodesic motion on the geometry of Nielsen complexity. Right, right. So there's the next thing here. So the Nielsen complexity is here with the cost function f1 defined in here. This is actually Javier's work, so maybe you can also ask him if you want. Here I'm just reviewing because I wanted to. You need a cost function, so the cost function is this one. Yeah, it's. These are not natural cost functions. So you have several possibilities for cost function that satisfy certain axioms, and the most natural one is called f2, which is the distance. But this f1 is the one that appears in this relation. So. That's right. That's right. And there's some generalization which was done by some people, including one of our collaborators, where you can add some extra term in the Hamiltonian that corresponds to the commutator, and correspondingly in the coherent state, you can ask, Jesus, I wrote this all wrong. A plus dagger L minus plus A0 L0, sorry. Anyway, this is, I just wanted to show that there's a connection between these two notions, because now I will make a connection between Krylov complexity and circuit complexity, and therefore all three will be related. So the circuit complexity is defined by a set of unitary gates, right? So we have a quantum circuit that involves some unitary gates, whereas Krylov complexity was generated by acting with a Hermitian Hamiltonian n times. So first, let's define the circuit complexity in a specific way, right? That's very essential. So we will use for that unitary transformations, but also superpositions. So the Hilbert space is assumed to be having n, what we will call beams, right? So the equivalent of qubits if you want. And then, but the reference and target space are all assumed to be in a single qubit or beam. I don't say, it's not literally a qubit, but it's the equivalent of a qubit. Then the three objects that we'll be using is a quantum beam splitter, which is a unitary transformation that acts this way. So you start in a beam k, and then you split it in, well, I guess k and k plus 1. The opposite, the superposition, you start in beam k and l, and you go back to just the beam k. And finally, a true unitary that acts on a single beam. So, yep. No, it's not. It's not copying. Yeah, the point is, I forgot right now the details, but this is something people can do in real experiments. So I don't remember exactly why this is not copying. I mean, yeah, it's not really copying because it's splitting. So it's like in a particular basis. Yeah. Oops, sorry. Yeah, well, okay. All right, so let me proceed. I'll show you a way to construct the target space. So the space of target space is defined by an action of unitaries on a specific vacuum state or reference state. So the space Sk is when I act up to k times with operator A. And then for this subset of states, we can find orthogonal bases where we act with a number m of unitary operators A. Then, how do we obtain the target space? Well, if I consider k equal to 1 in here, in S1, I can act with these three operations, the beam splitting, the superposition, and the unitary, to construct in the same k0, right? So I obtain in the same state k0 a generic state, so that the arbitrary state becomes this k0 and k1. So k1 having a single A. And in S2, again, in the same beam, we act in the same beam, but now we can act with two unitaries, and the corresponding target space is obtained by arbitrary combination at k0, k1, and k2 that are obtained from this object in this way. And finally, the issue of computational cost. That is a little bit tricky because we have to make some assumptions here. So the assumption, the first assumption is that we have to assume that the beam splitting and beam superposition have no cost. That's one way to think about it, is that the cost of A, of the unitary operation, is much larger than the cost of splitting or joining of the beams. And then we can just set the cost of the unitary to be 1. Which means that then the complexity, circuit depth complexity, is really, as usual, the number of gates. And with our choice of the object Cn, which contains up to a to the n, we could have chosen to be the computational cost of Ck to be k, but rather we'll take this slightly more, different cost, which is k times the probability of psi having passed through Ck, which is, and then summed over k, of course. Yeah. The way we've constructed, so that's why we. Oops, just sorry. Sorry. So that's why we've defined these objects. So in here we have the cost of the operator A is 1, but then you have to consider the arbitrary state, which is constructed out of these C hats, which themselves involve the operation of K's. Of this case, we'd have up to A. So we have the complete set of target space, a continuum set, right? And so that is, so we want to say that the notion is related to the classical notion of the number of gates is the complexity, but that's why in the end we take the cost to be this function that is really continuous. It's not n times anymore, right? This was just a precursor. So I want to say, well, the cost of an operator A is 1, but now the actual cost involving the continuous target space is this. And now this is really a continuous object, so there's no more epsilon involved, okay? But then the complexity is the minimum cost over the parameters, alpha and betas, right? These were the arbitrary alphas and betas. And once you do the minimization of this cost, you find that the cost of C1, C2, and minimization, sorry, you find that C1 at the minimum is equal to this, C2 at minimum is equal to this. So if you look, so C1, for instance, C1 had this parameter alpha 0 and alpha 1, right? Minimization means that alpha 0 is 0 and alpha 1 is 1, and so on. And so the complexity, which is the minimum of the parameters, amounts to this formula. So once the minimization is done, the complexity amounts to this formula. And now suddenly this starts to look like the formula of Krylov complexity, which was an algorithmic formula in the Krylov basis, right? Except, instead, so this would be exactly the Krylov formula, except I have this basis little kappa n instead of big Kn. So it's like the Krylov complexity, except I have this basis, which is found from unitary transformations, right? So I acted with unitary gates A, and I obtained this basis kappa n. Instead of, like in the Krylov basis, was obtained from action of n times action of a Hamiltonian, which is Hermitian, not unitary. So, and as a result, you can check that the unitary gate in this basis is not tridiagonal like the Hamiltonian is. However, there's a way to relate the two, which is to take our unitary gate A to be e to the minus I delta h, and take delta to 0. Right? So, this is dying. Okay, so this is a unitary, but if I take delta to 0, this is 1 plus Hermitian, right? So, so the Hermitian Hamiltonian is what gave the Krylov basis. So intuitively, this is the right picture, and we can check that indeed this is what happens. So, yeah, this. So in the for K1, for instance, we obtain this, and so as delta goes to 0, we obtain this relation, and so there are higher order terms that I dropped here. And so in here, I have just one action of the Hamiltonian, which is Hermitian. Yeah, I think the battery of this thing is dying. It doesn't seem to be doing anything anymore. Oh, no. Well, okay. Yeah, finally it changed. Good. Well, maybe until the end it works. So for K2, we got a similar picture here, like I wrote over there. And so as we see, K1, K2, kappa 1, kappa 2, and so on, orthogonalize to the Krylov basis K1, K0, K1, K2, and so on. So in the end, in this delta goes to 0 limit, we have that this operator involving kappa n goes over to the Krylov operator involving Kn. Yeah. Right, but okay. So so this is the first order issue, but then we'll try to keep delta finite and then see that when delta goes to 0, we get the right result. So. Yeah, so yeah, let me see. I'm not sure if I need this exactly, but let's consider now the time evolution. So let's consider that psi of t, which is the target space, really is obtained by time evolution with a Hamiltonian. Then we obtained a bunch of formulas for some matrices that we define, and for the return amplitude, which is given in terms of this action with E minus I tau h. But more importantly, let's look at the motion in the case of a group for which there are explicit analytical results. So for SU2, for instance, let's consider this Hamiltonian being the sum of J plus and J minus, and the initial state to be the highest weight state. Then one finds a certain formula for the return amplitude. And if we, just for ease of calculation, we look at the spin 1 case. Then after doing some calculations, we obtain that the complexity, depending on this parameter delta as a function of time, is this long formula. But if you see, if I take delta to 0, what I obtain is actually just sine squared, which is the correct result for j equal to 1. So this is an explicit example in which we see that there's no, if you want, there's no singularity in the delta going to 0 procedure. It's smooth, and the result at delta equal to 0 is obtained by just by taking it smoothly to 0. All right. The second part of this talk is about a different relation. So until now is something that is been on the archive. This is work in progress now. So I want to write the Krylov complexity plateau in terms of some instanton-like factor. So first, I want to rewrite the formula for the Krylov complexity in terms of some path integrals, which I will then try to argue that in some cases reduced to instanton factor. So in the Krylov complexity, we have this psi n of t, which is the projection of psi of t onto the Krylov basis. But we can introduce an identity in terms of coordinates x and do the usual and obtain this formula. And then for this transition amplitude between for transition amplitude between x and x prime of the e to minus I h t, we have the standard path integral formula derivation that everybody knows. So therefore, we can write a formula for the complexity that looks rather ugly, but involves this path integral. Now, let's think about what that implies. If I didn't have the integrations over the initial and final positions, then the path integral, we would say that the path integral has a saddle point at the classical action if there is a classical path. And if there's no classical path, there's a quantum mechanical instanton, E minus S instanton. The instanton in the simplest case is motion in the inverted potential in Euclidean time. And so in the simplest case, one thinks of the instanton as you look at the inverted potential, minus V, and you go between two maxima of minus V via minimum. So it starts at minus infinity here and go at plus infinity here. And in the real potential is a motion between two minima via maximum. However, in the general case, when I'm not talking about minima, there is still a notion of the instanton. You can see Landau and Lifshitz quantum mechanical books, for instance, where you go from the initial to the final point via pole in the potential. And so I'm saying that now the last thing to do is to integrate over the initial and final points and take time to infinity and consider chaotic systems. If all these things are done, then I will have this wildly varying phase e to the I s classical. And when integrating it, that means for the classical chaotic motion, the classical motion should average to 0. So I said that certainly for some initial and final positions, there's a classical path. But because we have a chaotic motion and we're taking time to infinity, this varying phase will give us a 0 result. And so what we will be left with is only the instanton factor, which appears when there's no classical path available. So the conjecture is that the sum of the classical paths sums to almost 0. It can be ignored. And we're left only with the instanton action. Of course, there's a caveat to that. I said the sum of the classical paths should sum to almost 0, but it's certainly not perfectly 0. So that means that E minus the instanton action cannot be too small. That's one caveat. It also cannot be, the SE cannot be too close to 0, because the action being 0 means sitting at a point, and that's certainly a classical path. So the caveat is that E minus SE cannot be too small or too large, and unfortunately I don't know how to quantify that, at least not yet. Then the potential must have at least two minima for us in order to have a solution that moves, so an instanton. If that happens, then by the integration over the initial and final points, saddle point approximation means that this should be peaked at the place where I have the minimal action, right? But the place that has the minimal action is the standard instanton between a maximum of the inverted potential and another maximum via a minimum. And so by this saddle point approximation, when I do this integral, I should have just sum of the minima of these instantonic factors. So finally, psi n, the projection of psi of t over the Krylov basis at infinite time should go over to this in the chaotic case. And so the Krylov complexity should become this constant value written in here that is now independent of time. It's purely topological, depends on the instanton action and on the minima of the potential. In the case of two minima, I wrote this slightly more explicitly. So it looks rather simple. The problem is it seems to be hard to work with. Yeah. The which?
Basically, when you're computing this survival amplitude, you will tend to a plateau, but it's a path integral over many trajectories, and in chaotic systems, these trajectories, as time goes, they proliferate, they grow.
Yeah.
You have all this issue that, and it's not really related to instantons, the plateau. I mean,
no,
in a random matrix theory, abstract random matrix theory, but
I'm saying so. So the notion of instanton now is the generic one, which you can find, as I said, in the quantum mechanics books of Landau and Lifshitz. So if you have an arbitrary initial and final position for which there is no classical path between them, which can happen, right? Then there is still an instantonic path between them, but that generically has a large-ish action, right? And I'm saying that there are two things that happen. The first is that because of the chaoticity of the motion, and because time goes to infinity, the sum of the classical path goes to almost zero. And the second is that the integral over initial and final points of the instanton action is peaked at the standard value, standard instanton that you learn about everywhere, which is between minima, right? Well,
infinite types of ways classical, no? Because and you can go infinite times and infinite,
well, yeah, okay. So yeah, I mean, I'm saying at least if you think about the one-dimensional case. So in the multi-dimensional case, it's harder for me to picture. But at least if you think in a one-dimensional case, right, there is certainly. If you start with generic initial conditions, there is no classical path that joins them. It's just there is only the instantonic path, a complex path. right? But yeah, in the multidimensional case, it's slightly more confusing. So. Yeah, so then we also looked at how to, we considered how to calculate at early times. Well, maybe I can, so it says time's up, but yeah. So, how to calculate at early times in order to do at least some calculation. Oh. All right. To do some calculations involving the complexity at early times. So one can compute the survival amplitude using just perturbation theory in time, applying a bunch of times the Hamiltonian, which at early times is possible. We can take, for instance, something like 100, 200 times, and then construct so psi n and the original psi 1, and from psi n recursively you can construct psi n plus 1. And we can also define a recursing procedure that is independent of the Lanczos coefficients an and bn, simply in order to make things easier to calculate numerically. And so one finds the complexity in terms of a bunch of objects defined simply algebraically, instead of having to solve a matrix condition to obtain the Lanczos algorithms and so on. So now we consider the toy model and some preliminary results, which, yeah, maybe I'm not sure how good they are. For the moment, they're a little bit inconclusive. But as a simple system, we considered two harmonic oscillators with an exponential coupling in between. So there's two versions that we considered, one with just A and A dagger, and one with exponential of alpha x1, x2. And if we put this G to be very small at small times, this would be this would be very small, whereas at large times this will grow. Excuse me. So in principle, this shows a chaotic behavior at large times. No, but x depends on time, right? So in practice, x1 and x2 are depending on time. Well, I wrote this with p, but of course it's x of t, x1 of t, x2 of t, and I'm saying if you start with some generic x1 and x2, initially this thing would be some constant, but if g is sufficiently small, you can neglect it, but then as time goes, this will generically grow, and then this will take us in a chaotic regime. I'm sorry? Well, if you, yeah, I mean, yeah, well, let's see. Yeah, so, yeah, I forgot right now why, but we can see this explicitly. Anyway, so in order to have a system with two minima, we have to have some condition on the parameters. And then we start with reference state. So at time t equal to 0, reference state that is Gaussian. So for the uncoupled harmonic oscillators, but then the coupling will of course modify this function. And here we have just some preliminary results for the early time complexity. It seems to go to about of the order of 10 to minus 4. Never mind what it is. In some particular case for a particular large coupling, we see that small coupling, excuse me, we see that this goes over to this becomes perhaps oscillatory. So I don't know. There's something to be understood there, but this is. So in principle, I would say that we need a formula for the plateau to give a higher result than this, and there are some preliminary results that seems to suggest that for a range of values of this, not too small, not too large, although this seems to be true, although it seems to be hard to prove numerically. And well, let me drop this, not relevant. Just to say that there were various, that there were previous formulas for the plateau, but perhaps of a different nature. So Javier and collaborators, for instance, showed that in the limit of dimension of the Hilbert space going to infinity, when you can define the ratio of the n of kn with the dimension of Hilbert space to be a parameter, then you can find for the finite temperature, the complexity of the thermofield double state is defined in terms of an integral formula. And first of all, this is necessarily at finite temperature, and I find it slightly puzzling the fact that both chaotic and this is true both in the chaotic and integrable regime. So anyway, just to say that this is not the only formula available for the plateau, but there's still a lot to be understood. So I hope our approach has something new. And to conclude, we've found that the Krylov complexity is algorithmic, but circumcomplexity is constructive, and the two are equal in some limit where the step size goes to 0. And also previously was found that Nielsen complexity and Krylov complexity are the same. So now these are also equal to circuit complexity, meaning there's a single notion. And we found that Krylov complexity can be obtained in terms of some path integrals dominated in chaotic systems by instantons for a certain range of instanton actions. And we're trying to test it in a toy model of two harmonic oscillator with an exponential interaction. That's it. Thank you. Thank you.